I think they'll let you do that.
So fun.
So, got a little introduction here. Suppose we have a reaction. The past, so really, chapter 13 was talking about thermodynamics and favorability. Chapter 14 dealt with spontaneity, and chapter 15 continues on that trend here. So, just a quick little refresher. We previously asked, will the reaction occur? And that was dependent upon not only just the thermodynamics or the favorability, but also on its spontaneity. Okay? And focus here. And we said that if it was a negative change in G, we said from a thermodynamic standpoint it was favorable. What two things went into change in G? You remember? Enthalpy and entropy. Okay, and we talked about, I mean, that was a difficult test too. I would say that's comparable to this one in difficulty. Okay? So, we talked about how change in S and change in H played a part, and we popped all that into one equation to get the overall big picture on thermodynamics and whether it was favorable or not. And then we talked last chapter about spontaneity, and a lot of that had to do with the activation energy. The activation energy was small. It was likely to be favorable. Right? So if the reaction is favorable and spontaneous, it will occur, but there's still a couple other questions that we might want to ask. So if you know that it will occur, what is our next question?
How much of the reactant turn into products?
Right? How much of the reaction will occur? Does it react a little bit? Does it react a little bit more? Does it react a lot? Does it react completely? How far does it react?
Till equilibrium.
It's so vague. Is it all?
Deep. Yes. In other words, will all the reactants turn into products? Up to this point, we have assumed, you guys, if you remember when we did stoichiometry, we assumed that the reaction went all the way to completion. Right? We went all the way to a limiting reactant runs out. Okay? Well, most of the time, that's actually not the case because of equilibrium. Now, and that's the focus of this particular chapter. So, not always. Sometimes it will go all the way to completion, but usually it does not. So, how do we describe where the reaction will end up? It will always end up at equilibrium. The big important topic of this chapter. Oh, so here's the question that we are going to hopefully answer in this chapter. How much of the reactants will turn into products? All right. So, up to this point, we have just used the forward arrow when doing separating reactants and products, correct? Right? And then you always saw that forward arrow in between reactants and products. Okay? What that signified was that reactants could only be producing products and not the other way around. But in reality, almost all reactants are reversible. What do you think that means?
Products can also produce reactants.
Okay? So I'm going to give you a theoretical reaction here to kind of talk about reversible reactions. And we're going to tie it in with what we learned last chapter with the collision theory. Let's say I have a bunch of molecules. Let's say I got 1,000 of each of these molecules. And I have 0 product molecules. Beginning of a reaction, right? Okay? Would you say that I have a lot of particles that could collide in the reactant side? Okay? More collisions means faster rate, correct? So over the course of time, these guys are going to collide, and their concentration is probably going to what? Go down. Right? They're going to react. And the concentration of my product is going to start going up. Right? That's a chemical reaction. Reactants are going to collide, hit each other, break bonds, atoms are going to rearrange and form products. Okay? Well, as this starts to react, the forward reaction is going to speed up or slow down? Slow down because I'm lowering the concentration. That means the forward reaction is starting to slow down. Start out way fast up here, reacting. Forward reaction is going really fast. Product or reverse reaction is not going at all. Why is the reverse reaction not going at all at the beginning? Yeah. It doesn't have any. Is 0 going to ever collide with 0? No. Okay? So we have all reactants, no products. So the forward reaction is really fast, and the reverse reaction's so slow it's 0. Make sense? But as reactants react, their concentration goes down and the rate starts to slow down. What do you think the product concentration is going to do? Go up, and then a reverse reaction is going to start speeding up. Until what?
Is everybody this?
No. Good guess though. But no, they don't do that.
Yeah, I've been thinking for the past 3 minutes on how to explain that.
That's what you came up with? Alright. So, the idea here is, where is this? Is it more products and little reactants? Is it a lot of reactants and little products? Where is it?
Equilibrium.
No, the rates are the same, but that doesn't mean the concentrations of both are the same.
Equals.
Everybody hear what I just said?
Oh.
Equilibrium is this. Listen. This is, if all the things you get out of this chapter, this is the one thing you should get out. Okay? Equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. That means the speed of the forward reaction is equal to the speed of the reverse reaction. Does that mean the concentration of reactants and products are equal? No. Could this be equilibrium where I have 100 of this and 900 of this?
Could be.
I could be at equilibrium there. I could also be at equilibrium a whole bunch of other possibilities. What?
100 with a comma.
Oh. Yeah. Does that make sense? So there's a variety of places where the rates could equal. Sometimes they're product favored, which just means more products at equilibrium. Sometimes it's reactant favored, which means more reactants at equilibrium. And there's only one spot where they can be equal. So the odds of the concentration being equal are very low. You guys understand what I mean by that? Could I have a whole bunch of number possibilities where these are different? Yeah. But only one possibility where they're the same. What is the same going to be in this context?
Same.
Well, what is the number?
900.
900 and 200 are the same?
What? Oh.
500 and 500.
I was so, okay,
If 500 reacts of each of these to produce 500 of this, that's where they would be equal. There's only one point where they will be equal. Concentration, number of particles. Okay?
Oh, is that what we're saying?
Just remember, what is always required for equilibrium? What did I say?
The rate.
The rates, the speed of the forward and the speed of the reverse are going to be equal. And as we progress here, we're going to go more into detail here. Equilibrium. Static versus dynamic we have. I think talked about this a little bit. Static usually doesn't require movement at equilibrium. Two forces balance each other out. They're not going to be moving. Okay? Dynamic equilibrium is the processes are still moving, but the net outcome or the net change is there is none. And I'll give you a couple examples here. Okay? These guys are pushing with equal forces. Is the car moving? Static. Have you ever heard of dynamic versus static stretching? What's static stretching? Not moving. Like you're sitting on the ground, you're reaching and trying to touch your toe. Or I'm reaching down trying to touch my toes right now. That's static stretching. Dynamic stretching is usually moving while stretching, like this.
I think the white guy's stronger.
Or high knees, butt kicks, things like that if you're familiar with any of the dynamics.
No.
Yeah. I am literally known as one of the most inflexible people on the
Are you for real?
Yeah.
If you
Worldwide, you're known?
I mean, I went to a physical therapist 3 years ago, and then went back to see him, and I didn't think he'd remember me, and he said, "Oh yeah, I remember you. You're the least flexible individual I've ever worked with."
Kramer.
And you gotta imagine, physical therapy, you see people all the time. No.
Okay, as far as you can go.
That is, I mean, I am in pain right here.
Kramer, I swear this
Anyways.
works. If you read a paragraph backwards, you can touch your face. No, it literally, it does, okay?
Okay, so force your balance, no movement
I
as occurs.
swear.
Come on. Static equilibrium, no movement. Dynamic equilibrium.
Oh no!
Okay? Now, so I know it's a silly picture, but what is it trying to represent?
Water's coming in at the same rate she's getting it out.
Yes.
Well, I feel like a hat would not.
I know, but the idea here is water's pouring in, and she's putting it out, and she's doing it as fast as water's coming in. Is there any change occurring?
No.
No, there's no net change in the amount of water in her boat.
So if you have like a thing that's doing this, is it always, it's just like always in there doing its thing, but it's just like you have it? What?
So I think what you're saying is, when I take two things and I react them, normally you would see evidence that the reaction's occurring, like bubbles or gas being formed, or something that a lot of energy given off. But after a period of time, it appears to stop, doesn't it? Like if you were to mix baking soda with vinegar, you would see bubbles, you would see a pretty vigorous reaction, and then it appears to stop. Well, guess what? It doesn't stop.
Is everything always reacting?
Well, that's not a reaction, but in theory, if you had a
And
chemical,
you have infinite energy.
that's not infinite energy. It's just going back and forth. No.
Seriously, Gage.
So if I put an acid and a base and mix them together, you will see a reaction, you will see it, but eventually you won't see it anymore. It doesn't mean it stopped. The net change is nothing, there's no overall net change. You still have molecules frantically going to produce products and molecules going backwards to produce reactants at the same rate. So it's happening very, very frantically, but we don't see anything because we don't see a change. Does that make sense?
Yeah.
Yeah, you wouldn't see the bubbles because you're not seeing a change. Okay? Crazy. And of course, chemical equilibrium is a dynamic process. Okay, the forward reaction and the reverse reaction rates are equal, so they are balanced. Okay? Doesn't mean they stop. It means they occur simultaneously at the same rate. And rate means what? Speed or how fast. So the forward reaction is reacting as fast as the reverse reaction is reacting. So products are being formed as fast as they are being broken down back into reactants. So no overall change, but still a lot is going on. Okay? It's like our government, a lot of work with no outcome.
Amen.
It's like me studying.
I love off-camera Kramer.
It's like me trying to cop shoes.
Yeah. Alright, here we go.
Mr. Kramer trying to play Fortnite.
Hey.
That was too far, too far.
I call my students that just dodge playing with me.
Where did you play last night? You said we were playing last night and you didn't.
You weren't on!
Yes, I was. I started at 9.
I said,
Oh, was your wife home?
no, we said 7 to 9.
Yeah, I heard that. I remember that.
Nice.
And I was on at 7, and nobody else was.
I had okay. I got
We're not arguing about this.
I got home at 7. Showered 7:15. Did homework.
That's fine. But we had agreed at 7 to 9, so
I've never. This is the first time I've heard it. You probably told Andrew.
Andrew and Steven both knew.
Okay, well.
And Andrew was never on.
Andrew's
Steven
not-
got on about 8:30. Was when I got off.
I got it at 9:15. And I played 2 games
That
ago.
makes sense why I didn't see you on. Okay? Specifically, the rate of the forward reaction equals the rate of the reverse. What?
You're salty.
I would be too.
Sorry.
Yeah.
Oh yeah, you had an agreement. Agreements go before homework. That's how it works.
Thursday
GPA
night
doesn't
was Batman
matter.
series at my house. Kramer, Thursday night. My house. Batman series.
I've seen Batman so many times.
Andrew, I haven't seen it. I've only seen it like
I've seen it.
Whoa, that's such a.
Everybody see that? I know you guys are we're all bickering over stuff that's really not that important.
Fortnite is important.
No, it's not.
Okay? That's why my brother.
Can you like this?
Everybody see that?
That's nice.
Yeah.
Reactants are producing products as fast as products are going back to produce reactants. Is there a net change?
No.
No! Okay.
It's the first one.
Like, why is this?
Okay. Now, this is also really stupid.
Nice.
The forward reaction always goes from left to right. Duh.
Really?
Okay. Don't get that wrong on the test, please.
Well, that's good.
Alright. Okay. Now, I've kind of already alluded to this. When I say shifted to the right or shifted to the left, this is before we've reached equilibrium.
Start fancy.
Because at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So if I say something is shifted to the right, what that means is the forward rate is faster than the reverse rate. You're probably going to want to pay attention.
Nice.
Let me state that again. The forward reaction is going faster than the reverse reaction, and so we're seeing a net change in a production of what? Products. If the forward is going faster than the reverse, you're going to see a net change of products being produced. If I say shifted to the left, that means the reverse reaction is going faster than the forward reaction, and so you're going to see a net change of what being produced? Reactants.
Then you'll never have equilibrium.
No, it'll eventually reach equilibrium, but I'm saying this is before it's been reached. Okay? So if I say shift to the right, at that moment, you're faster going to the forward reaction. But as you start reacting reactants, right? So say this is the forward reaction and this is the rate of the reverse reaction. Right now, the forward is faster. But as this starts to react, this starts to go up, and eventually they still will reach equilibrium. This just means before equilibrium is reached. If I say shift to the right, that means it's going to produce products and eventually it will reach equilibrium. If I say shift to the left, that means more reactants are going to be produced until they reach equilibrium.
So dynamic is, or static is like forces,
Yeah.
and then static is with like.
I mean, there's other terms that you can use static for, but forces is usually a good one to use. Okay, there's other things that are dynamic than just chemical equilibrium, but this is one of them. Okay? Okay, so this is some things that you could say about a shifted right situation. More products are going to be formed. This does not mean there are more products at equilibrium. Be careful. This just means at a certain point, if I haven't reached equilibrium, more products are going to get produced until it reaches equilibrium, but I could still have more reactants at equilibrium than products. For example, in this situation, which way do you think it's going to shift? To the right, because I have none of this and all of this. But let's say it reaches equilibrium where I have 100 of this and 900 of both of these. So originally it shifted to the right, but at equilibrium, what has more concentration? The reactants. So be very careful. When I say shift to the right or shift to the left, it's before equilibrium is reached. It doesn't tell you anything about what the concentration is at equilibrium. Okay, this is one of those deep concepts here. Let's progress as we continue going here. So we are going to talk about 3 possibilities where equilibrium can occur. Now, I'm going to take a step back. I just talked about what we can talk about from before equilibrium standpoint. The rest of what I'm going to talk about today is at equilibrium. What is true when you're at equilibrium?
Both forces are
Forces?
both energy.
Guys, what is happening at equilibrium?
Processes are going to some.
They're all equal.
What are the processes?
The rate.
Forward reaction and reverse reaction are the processes. And when the forward reaction rate is equal to the reverse reaction rate, you're at equilibrium. That means rates are the same. Does that mean concentrations are the same? Okay. So here's one situation. I mix some stuff, a reaction starts to occur, equilibrium is established. These arrows continually going means that these are being produced as fast as they're going back to form reactants. Okay? We are at equilibrium. Notice, which has a higher concentration?
The top one.
The reactant.
The reactants. You would say this is a reactant-favored reaction. Okay? That's one possibility.
Oh, you said it's favorable? What is that?
No, I said reactant favored. At equilibrium, I have more reactants.
No.
Okay?
So how do
You could say the reverse reaction was favored. Would that be a logical, another way of saying it?
Yeah, but how does C get to A and B?
What do you mean? How does it
It's a reverse reaction, it breaks apart and goes back to
Yeah, but it's not favorable for C to break apart to A and B.
It's not as favorable, but it still happens. When I say favorable, I don't
Both
mean
can't be
can't.
favorable.
What?
They both can be favorable, right?
So, when we talk about favorability, we're talking about likelihood. We haven't even addressed equilibrium up to this point. So when we talk about equilibrium, it doesn't mean that neither will happen. It means that one is going to likely happen faster than the other. And that's why you can reach equilibrium at a point where you have more reactants than products, or you could reach equilibrium at a point where we have more products than reactants, depending upon which one's more favored. It's not so much favored or not favored, it's which one's more favored in the context of equilibrium. Okay? So we could say that the reactants are favored, we could say the reverse reaction is favored. That's possibility one. Okay? Happens simultaneously. Okay, here's what it would look like on a graph. At the beginning, I have all what? And no what? Okay? They start to react. Okay, the concentration goes down, the concentration goes up. So the rate of this gets slower, the rate of this gets faster until they what? Reach equilibrium, and we see no net change or difference. Yep. Okay? Which one was favored though? The forward or the reverse based on this?
Forward.
No.
What do I have more of at equilibrium?
Reactants.
Reactants. Okay? That means in the rate of these guys, the reverse won out. Okay? Here's the second possibility. I pour them in. Equilibrium is reached. This is the most unlikely.
It looks like,
That's not so likely. But okay.
Yeah.
Is it?
Yeah.
Yep. You're right.
Alright. So the reason why I say this is the most unlikely is what's true about equilibrium.
Well, both, no wait.
They're the same amount.
Same amount, same concentration. Remember how I said there's only one place where you can have the same concentration? But you can have multiple places where you have more products and multiple places where you have more reactants? You can have 10 and 1, 9 and 2, 8 and 3, and so forth. But the only place where they're going to be equal is one point. Now, equal concentrations. Equilibrium is always equal what?
Great.
Rates. Difference. That's the thing that gets most messed up. Is you think same rate means same concentration. No, 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 no. It can at one specific point, but usually not. Okay? We would say that neither side is favored. Because I produced equal amounts of both. Okay? Again, same slide you've seen. Okay, here's the third possibility. And you can probably figure out what the third possibility is. I said reactant favored, I said neither favored, and now we're going to be product favored. Okay, still, equilibrium is reached, rates are the same. However, the place where the rates are the same is in a different location. Stay with me. You have product favored because the concentration of your products is higher at equilibrium than your reactants. Another way of saying this would be the forward reaction is favored. Now here's what a concentration over time graph looks like.
Let's go fish.
Did we still start out with more reactants and no products?
Yep.
But in the end, I had what?
More products.
But now, did this go all the way to completion? No. Why? How do you know it didn't go all the way to completion?
It starts spreading back down.
This is not what?
Flat.
It's not zero.
Oh.
If it were completion, this would be all gone, and I'd have a max amount of products. So when I say completion, I mean completely react all of the reactants. Yes, this is product favored, but it does not mean that it went all the way to completion unless this is all gone. Okay, last, I think for one more slide I just want to show you. This is just kind of summarizes everything. Remind me tomorrow, maybe why don't you take a picture of this? It might be helpful. This just summarizes all three possibilities.
Are there ones where they're not reversible?
There are some, but we're going to spend time, in this chapter we're going to talk about all reversible reactions. Okay? Alright, we are done for today. If there are things you're struggling with, do not let a day go by where you don't get them answered by me.